So what we were doing was random walks, right? And we had written down the governing equation that the probability of a random walk. So this was some discrete random walks. So this was discrete random walks. So the probability of a random walk to be at location R we had written as sum. Right. And then by introducing the discrete Fourier transform g n of k equal to sum over all r values from minus infinity to infinity e to the power of I k r p n of r, right? I had used plus. Yeah, I had used plus here. We had evaluated this g n of k to be u k to the power of n to be p e to the power of I k plus q e to the power of minus I k whole to the power of n when my random walk had started from the origin. So that was my initial condition. Yeah. So P0 of R. So given that P0 of R was delta of R comma 0. Huh? Which line is there an issue? This one? Next one? Huh? G naught. Huh? Thank you. But yeah, okay. So there was this G naught of K, and this implied that G naught of K was 1. So therefore, that was my Gn of K. Therefore, uk to the power of n. And then I inverted this. So we took the inverse Fourier transform Pn of R was 1 over 2 pi minus pi to pi e to the power of minus I k r Gn of k. Gn of k. So that gave me my binomial. Right, nc n plus r by 2 p to the power of n plus r by 2 and q to the power of n minus r by 2, right. So this was my Pn of r, and here someone, I think Sibgat, was asking why minus pi to plus pi. So sorry about that. So this is because this is a discrete Fourier transform. So essentially these are these k's access inverse wavelengths. So you cannot go smaller than a single lattice site. So if you're hopping, your lattice site is 1, you cannot go smaller than that, which means that your k, which in the continuous case goes from minus infinity to infinity, in the discrete case is minus pi to pi. The other way to think about it is that, here what you need are these Kronecker deltas, remember, and the Kronecker deltas delta ij R is this object minus pi to pi, right, e to the power of I k delta of n comma 0 I k n, right, whereas your dk, whereas your if you had a continuous Fourier transform, you would have a Dirac delta of whatever Dirac delta of x, which would be minus infinity to infinity e to the power of I k x dk. So, because you have this discrete, your lattice, you can only hop, you cannot access all of space. So, you can only hop in steps of 1 that restricts what values of the wave numbers you can have, and in this case it is minus pi to plus pi. You can check this by substituting in that sense. So, if you take I have my u hat of I have my gn of k over here. So, essentially let me see. So, if I have some function u of r, I can calculate the discrete Fourier transform u hat of k, which is this thing, sum over r e to the power of I k r u of r, and then I can calculate the inverse transform. So, u of r, and I can show that, let me see. So, if I had to calculate the inverse transform, so minus pi by to pi. So, let me just calculate this integral, minus pi to pi u hat of k e to the power of minus I k r dk by 2 pi. So, I am just calculating the inverse transform of this from minus pi to pi, and then if you substitute for this u hat k, so integral minus pi to pi sum over r, let me see, sum over r, let me not call it r, let me call it some dummy variable, r prime, from minus infinity to infinity, u of r prime e to the power of I k r prime. So, this thing, so that is my u hat of k, then e to the power of minus I k r dk by 2 pi, whatever else is left, right. So, here is my discrete Fourier transform. I take the inverse. For u hat of k, I just substitute this definition, r equal to minus infinity to infinity, but a discrete summation. And then if I do this k integral first, right. So, if I do this k integral first, r prime from minus infinity to infinity, u of r prime integral minus pi to pi e to the power of I k r prime minus r dk by 2 pi. That is my definition of the Kronecker delta over here, right. So, this is nothing but sum over r prime from minus infinity to infinity, u of r prime delta of r comma r prime, and therefore, what you are left with is essentially u of r, right. So, this is just to show that if you want to get the u of r by taking the inverse transform, the correct limits is minus pi to pi because of the discrete spatial structure in this case. So, that is that. All right. So, we had done this Pn of r, and then we had said that because of central limit theorem, which says that if you have independent and identically distributed random variables in the large n limit, you will converge to a Gaussian. We said that Pn of r in the limit that n goes to infinity. So, if you waited long enough, this would be Gaussian e to the power of minus n, right, sorry, r minus Gaussian in r. So, r minus n p minus q whole square by 2n 1 by square root 4 pi, right, 2 pi n, sorry, not 4 pi n, 2 pi n. My variance is n, so this is just 2 pi over n. So, this is what it would go to in the continuous limit. So, this is what we had done last day. Then, so let me now resume. So, this part is fine, right. So, let me now resume. So, we had calculated this Fourier transform or the characteristic function. We had calculated the characteristic function, which was the discrete Fourier transform characteristic function. The other thing you might want to calculate is the generating function. Is the generating function the discrete, which is the discrete Laplace transform. Okay. So, this I call as gamma of r comma z, okay, sum over z to the power of n Pn of r. So, let me call this Pn of r. Okay. Pn of r is the probability to be at r after n steps. Multiply that by z to the power of n, take a summation over all possible n values 0 to infinity. So, this is like your Laplace transform, but with except this integral is replaced by a discrete summation. So, this is the discrete version of the Laplace transform. Okay. And therefore, if you write out this summation, this is like, what is the probability to be at r after 0 steps plus z times what is the probability to be at r after 1 step, and so on and so forth. Right. So, in principle, you can if you know the generating function, you can generate any of these probabilities by taking, again, exactly like in the case of the characteristic function, by taking higher and higher order derivatives, right. So, if you take dm dz to the power of m of this gamma r comma z, and divide by m factorial, you would get Pm of r, right. What is the probability distribution after n steps? Evaluated, of course, at z equal to 0, set all other terms to 0, right. So, exactly just like by taking the derivatives of the characteristic function, we generated moments of the probability distribution, the corresponding order moment. By taking derivatives of the generating function, one can get these probability distributions at different instants of time. Okay. Why do I want to do this? So, maybe I want to calculate some quantity. So, I will calculate this just to motivate it. So, I want to ask, so I am thinking about a one dimensional random walk, right. So, here is my lattice with discrete sites. Here is my random walker. Let us say it has started from the origin. So, this is my origin, and it is hopping to the right or to the wherever it is, to the left, and so on and so forth. And I wanted to ask that, will this, having started from the origin, if I waited long enough, will the random walker come back to the origin? Okay. So, this is a property called recurrence. So, recurrence. Okay. And that we will try to calculate from this generating function. So, what do you think, by the way? Random walks are sort of familiar. If I waited long enough, will the random walker come back to the origin? Huh? With? There is probability that it will come back. So, then, okay, so let me rephrase this question. If I waited long enough, am I guaranteed that the random walker will come back to the origin? No. Okay. All right. So, good. So, let us try to now calculate it, and then we will see what we get when we calculate. Okay. All right. So, I have my generating function. Let me calculate the Fourier transform of this. Gamma hat. We calculate the Fourier transform of this. So, here is my gamma. So, r equal to minus infinity to infinity, e to the power of I k r, gamma of r comma z, right. That is my Fourier transform, which means I have sum over r equal to minus infinity to infinity, e to the power of I k r, another sum which is a sum over n equal to 0 to infinity Zn Pn of r, right. I have just written out the gamma of Rz. Now, if I do this R summation first, e to the power of I k r Pn of r from minus infinity to infinity is nothing but your characteristic function, right. So, this is nothing but sum over n equal to 0 to infinity z to the power of n times your characteristic function g n of k, right. And Gn of k I know, if I have started from the origin, my Gn of k is that object to the power of n, right. So, this is sum over n equal to 0 to infinity z to the power of n, and let me just write z u of k whole to the power of n, right. This was my u of k, remember. So, this is my u of k to the power of n g0 of k, right. U of k is just this quantity p plus q. What is this? What is this summation? X to the power of n sum over n, 1 by 1 minus x, right. So, 1 by 1 minus z u of k. Okay. Now, if I know the Fourier transform of this generating function, I take the inverse Fourier transform, I will get this gamma r of z. Huh? 1 1 1. So, I have particle started from the origin. Okay. So, if you want, you can write Gn of k given that whatever del starts at origin, starts at 0. All right. So, now I want to calculate, I can take the inverse Fourier transform, gamma of r comma z is equal to 1 over 2 pi integral dk e to the power of minus I k r times that object 1 by 1 minus z u of k minus pi to plus pi, okay, and u of k was now you can think of this for of course any general p and q and so on, but for this special case it becomes, if you are, let me see, if I just want to calculate this object, that if I want to if I say that let r equal to 0 and let me consider a symmetric random walk, which means that p equal to q equal to half, okay, so that I can pull this half out over here and combine this, then this integral you can do very easily, and then so then you will get gamma of 0 comma z symmetric random walk is 1 minus z squared to the power of minus half. Okay, so you can evaluate this and check that at least for this case, for the symmetric case when p equal to q equal to half, you can do this integral and get this generating function gamma 0 of z. Okay. Now, what I want to calculate is this question that we set out, that is the random walker guaranteed to come to the origin. So, how do I get there from here? So, I have calculated this. So, let us think about what this object is. What is Pn of 0, right? Pn of 0 is the probability that my random walker is back at the origin after n steps, right? That is my Pn of 0. And then now it could come back to the origin after any number of steps, of course, and there is some probability associated with that. So, if I think about this object, so this is P0 of 0 plus P1 of 0 plus P2 of 0 and so on. So, this tells me what is the probability that the random walker is at the origin after 0 steps, what is the probability it comes back to the origin after 1 step, what is the probability it comes back to the origin after 2 steps, and so on and so forth. If I summed up all of this, this gives me the average number of times the random walker returns to the origin, right, after any step, does not matter, after any step. Okay. So, this is then, so this quantity is then my mean number of times my random walker returns to origin. Right? Is this fine? That this quantity sum over n Pn of 0 is the mean count of times my random walker returns to the origin. What is this in terms of the generating function? Sum over n Pn of 0 essentially means that I set r equal to 0, I set z equal to 1, right. So, therefore, this object is nothing but gamma of 0 comma 1, right, because if I set z equal to 1 over in that definition, I just get this Pn of 0. So, this is the probability any term. So, this is the probability that you return to the origin after n steps. With that probability, you count one return, right. This is the probability, the next term is the probability that you have returned after n plus 1 steps, and again one return. So, if you summed up all of these probabilities, it is the mean number of returns to the origin, right. Think about this, that this is then the mean number of times that you return to the origin. Okay. So, now that I know that I just need to calculate this, I know this general solution. All I need to do is take the z tending to 1 limit over here. So, what happens to this z tending to 1 limit? So, this is limit z tending to 1 from below 1 by square root 1 minus z square. What is this as z tends to 1? Infinity or 0? Who says 0? Who says 0 is fail? This is infinity, right? As z tends to 1, you blow up. What does that mean? It means that if you waited long enough, you are guaranteed to return to the origin, okay, right, because the number of times you return to the origin approaches infinity, which means that any individual random walk that you consider, even if it has gone very far off, does not matter. You sit here and wait and wait and wait. With probability 1, your one dimensional random walk is guaranteed to come back to the origin. So, this is called as a recurrent, this is called recurrence. In symmetric random walk, of course. Thank you. For a symmetric random walk in 1 dimensions, if you waited long enough, you are guaranteed to come back to the origin. You could ask this for higher dimensional random walk, still symmetric. So, for example, you could ask this for a 2-dimensional random walk, right. So, now you are walking on a lattice. Let me again take a discrete. So, here is my particle. At every step, you can go up, right, down, left, right, each with some probabilities. Let us say symmetric. So, let us say 1/4, 1/4, 1/4, and so on, right. So, this 1D process, but now generalized to a 2D case, to the case when the random walker is walking on a 2D lattice, and then asks will it come back. And if you do this, maybe I will try to see for an assignment. If you do this, you can show that the 2D random walk is also recurrent. That means you are guaranteed to come back to the origin if you waited long enough in a 2D random walk. On the other hand, if you did a 3D random walk, that is not recurrent. So, if you do a 3D random walk, there that number is no longer going to be infinity. So, this is known, these are recurrent random walks. For the case of a 3D random walk, it is known as a transient random walk. Okay. So, in this case, you are not guaranteed to return to the origin. So, essentially, I mean, there is no, at least I know of no way to motivate why it should happen, why it is recurrent in 2D and not in 3D, but it essentially has to do with the number of ways that you can escape. So, in this case, you have 2 options. In the 2D case, you have 4 options, and in the 3D case, you have 6 options. And then there will be some weight to come back and some weight to go away. So, a balance of these weights determines whether you are recurrent or transient. Then you have to work it out essentially and say that which coordination number essentially takes you from this limit to that other limit. So, it turns out that the 2D run in the 2D case it is recurrent, but in the 3D case it is not. So, okay. However, note that just because it is guaranteed to come back to the origin does not mean that if so. Okay, so in the 1D case, therefore, I am saying that the 1D random walk, or rather, we showed that the 1D symmetric random walk is recurrent, which means that you are guaranteed to come back to the origin. So, you could ask that, well, what is the average time that I need to wait, right? So, I start at the origin, how much should I wait until I come back? I know I will come back because that probability is 1. So, how much should I wait? And it turns out that this thing time blows up as well. So, you may have to wait infinitely long, but if you waited infinitely long, you are guaranteed to come back. So, when we are doing time at towards the later half of the course, first passage times and so on, we will maybe try to come back and calculate this as well. So, this is about recurrence and transience. All right. Is this fine? Yes. For this symmetric random walk, one can define random walks with different rules. In this case, in this sort of a random walk, left, right equally, like all directions equally probable, it is applicable up to 2D, not in 3D. One can define different sorts of walks. This is the simplest, but you could take hops where the probability of the hop depends on the length of the hop itself. So, you could take long range hops, for example, and then so those are called, at least one example is called Levy walks and so on. So, there that property you would have to rework and see what happens in those cases. Okay. So, therefore, for these discrete sort of random walks, you can work with these characteristic functions, generating functions, try to calculate these analytically, and from there try to predict what are the sort of physical properties of the walk. The other option is to sort of go, if your system is large enough, you can go to continuous random walks. So, you can take the continuum limit of these and go to continuous random walks. Okay. So, remember what did I have in this case? I had Pn in the discrete case, I had Pn of r is equal to P Pn minus 1 of r minus 1 plus Q Pn minus 1 of r plus 1, right. So, I have a discrete lattice at every time it can hop to the right or it can hop to the left. let me take this, since we are taking the simplest cases, let me just take the simplest case, symmetric random walk, okay. Half and half. If I am taking the continuous time, if I am taking the continuous limit, the continuous space and continuous time, I could ask that, well, what is the probability? The analog of this would be that what is the probability to be at some position x at some time t, right? It's like what is the probability to be at r after n steps? This is like what is the probability to be at x after time t, where both of these are continuous variables. And you can again frame it in terms of this, something like this, that what is the probability that I was at one step to the left, so x minus delta x, right, at time at one step previous in time, so t minus delta t, plus half probability that what is the probability that I was one step to the right, x plus delta x at t minus delta t, right. So, this is still like the discrete version, except that whatever I was calling as one lattice, my lattice spacing was 1 in the earlier case, here my lattice spacing is delta x, my time steps also was 1 delta t, here I have explicitly written a delta t. Now, I can see if I expand this out, if I do a Taylor series expansion, I take delta x going to 0, delta t going to 0, I will reach the continuum version of this, right. So, this is like, so if I just write it out, so this is half p of x comma t, right, minus delta x del p del x plus delta x square by 2 del 2p del x2 minus delta t del p del t, right. That is from this first term, p of x minus delta x, t minus delta t. And then similarly from the second term, I do another Taylor series expansion, this 2 variable Taylor series, right, plus delta x del p del x plus delta x square by 2 del 2p del x2 minus delta t del p del t, right. So, I do second order in time, first order in, sorry, I do second order in space, first order in time, because as you can see the first order in space terms, they will cancel each other. Here I have a minus delta x, here I have a plus delta x. So, once I sum, these two will cancel. So, essentially I am just keeping lowest order terms, lowest order term in time, lowest order term in space, and this px, this half plus half cancels this over here. So, this will cancel this and this. So, then what I am left with is this equation, that del p del t is times delta t is delta x square by delta t del 2p del x2, right. Del p del t is delta x square by delta t in space, yes. Cross terms, that is one higher order, right. So, I am keeping lowest order. So, you are saying this delta t delta x sort of a term, cross term, right, but that is one order lower in my expansion, because that is two deltas together, right, one delta. Okay. So, true, but the thing is that actually that also does not matter, right, because that also cancels, because the term the sign of that term from here and from here, that will also cancel, right, because there is a plus delta x, there is a minus delta x. So, that cross term also does not contribute. Okay. So, to lowest order is this, right. Now, of course, I have to take this limit that my delta x goes to 0 and my delta t has to go to 0. Am I missing a? I am missing a 1 by 2. Thank you. So because there is a 2 over here. So, this half anyway. So, I have to take this limit delta x going to 0, delta t going to 0, and I take this continuum limit. So, my continuum limit is delta x goes to 0, delta t goes to 0, and I take this continuum limit in such a way that this quantity d, which is limit delta x going to 0, delta t going to 0, delta x square, so delta x square by delta t, this is finite. Okay. And then what I am left with is this continuum version of this equation, that del p del t is d times del 2p del x2. Right. So, this is my diffusion equation. So, I started with a random walk. I let these individual, I started with a discrete random walk. I let these individual jumps go to 0. I let this time increment go to 0 in a controlled fashion, such that this ratio delta x square by delta t stays finite. And in this continuum limit, I arrive at the diffusion equation. So, the diffusion equation is nothing but the continuum version of this random walks, where you have no memory. At every time you are taking this random decision whether to go left or right, top or bottom, whatever be the dimensionality of your random walk. If it was not a symmetric random walks, if I had not started with a p equal to q equal to half, what would I have had? I would not be able to cancel this. So, I would have a p over here, right. I would have a p over here, I would have a q over here, which would not be equal, which means I would be left with a term in addition to this, something like a p minus q times delta x by delta t del p del x, right, which looks like what? Which looks like something like, so this is dimensions of what? Of a velocity, right. So, that would give me my advection diffusion equation, where you have a v times del p del x term over here, right, and the velocity is proportional to the asymmetry in your hopping rates. If one direction you prefer to move to the right a lot, then you will have a higher velocity towards the right. If you prefer to move to the other direction, you will have that velocity. So, that would give your advection diffusion equation or drift diffusion equation. Yes? No. So, essentially I agree if I were doing an agnostic thing perhaps, but I know that the correct way to take the continuum limit is this fashion, that delta x square by delta t in this continuum limit stays finite. Having said that, I will take all terms up to this order and anything that is larger than this, which is why I will of course have to keep the delta x, but I would also keep this, because I know that the correct way to take the continuum limit is that this delta x square by delta t also stays finite in the continuum limit. So, I would keep this term and terms which were higher order than this, but lower than this, but I would not keep any subsequent higher order terms. So, the correct way therefore is to do this is to expand up to second order in space and up to first order in time, and that will give you in this symmetric case just a diffusion term, but in the asymmetric case a drift term and a diffusion term. You are saying in the continuous case? In which case? But for which random walk? Like in one dimensional random walk? In one dimensional random walk we said it's recurrent, right? So, it's guaranteed to come back. But what you're not asking that, you're asking something. What are you asking? So, yes. So, if you're saying that I have started from some position delta of x comma 0 at the origin, and you're asking what is the probability that I never return here, right? Is that what you're asking? Yes, that goes to 0 for the 1D random walk, because you're certain to come back. So, therefore, the probability that you never come back. Correct. correct. If I do not take this delta x going to 0, no, but I want to take this limit because I am looking at the continuum analog of this random walk. If these were not small, then of course I will stick to the discrete random walk. So it's in some sense, if I have bacteria that is swimming, right. So I have an E. coli that is swimming in some fluid medium, it is doing something, it can access all of this space, right. So it can access all of space. So there is nothing discrete about space in that sense at the length scale of the E. coli. So therefore, if I am thinking of a random walk of E. coli, then I would treat it as a continuous random walk and use the diffusion equation. On the other hand, maybe if I am thinking of even then, anyway, so let me say that I have a DNA sequence, you know, A, T, C, G, some sequence, and I have a protein, let us say RNA polymerase, that is moving along this DNA sequence, right. When it is moving along this DNA sequence, what it means is that it is either bound to this base, or it is bound to the next base, or it is bound to the next base, and so on. So there is an underlying discreteness of the lattice that this RNA polymerase explores, right. In this case, perhaps the more appropriate language to use would be that of a discrete random walk. See it, but again, even there, for example, if you were looking at, if your DNA chain was very small, very large compared to the base pair spacing, and remember this spacing, I hope I said at some point, is roughly around 0.33 nanometers, right. So if you were looking at a DNA, segment of DNA, which was very long compared to this 0.33 nanometers, then you could make this assumption that delta x is small enough that I can use the continuum limit. On the other hand, if your DNA was short and you were looking at this sort of a protein motion problem, then maybe you want to stick to the discrete limit and, you know, think in terms of discrete random walks. No, right, because if I think about this, so I have one term which is of order delta x, which is my del p del x, right, with some p minus q in front. Then I have another term which is delta x delta t, del p del x del p del t, again with something in front, and then I have this delta x square del 2 p del x2 plus delta t del p del t, correct. So now I want to write the del p del t on one, I bring the del p del t on one side, I divide everything by delta t, so that so I get a delta x by delta t, I get a delta x square by delta t, I get this by delta t. So this is my velocity term. Here I just have something which is delta x which goes to 0, nothing to balance it. Here I have delta x square by delta t, which is my diffusion term, but this term still goes to 0, right. So the cross term still does not appear in the picture. All right, so we get the diffusion equation as the continuum limit of our random walks, and now we can solve the diffusion equation. There are many ways to solve the diffusion equation. I'll just solve it in one way, in other ways, right. So I'll solve it using the Fourier transform. So I want to solve this diffusion equation, so solution. So let me take the Fourier transform. So p tilde k of t is e to the power of I k x, e to the power of I k x, p of x comma t dx minus infinity to infinity, right. So that is my Fourier transform, and therefore of course my if I want the probability distribution itself, it is just the inverse Fourier. So 1 by 2 pi minus infinity to infinity dk e to the power of minus I k x p tilde of k. All right. So, I can take the Fourier transform of this equation itself, right. So, what is del 2p del x2? So, del 2p del x2 is what? Is minus k square, because I bring 2 times ik. So, minus k square integral p tilde k comma t e to the power of minus I k x dk minus infinity to infinity and 1 over 2 pi. So, that is my d2. So, I take this equation, I take a second derivative with respect to x. So, on the left hand side I get this, on the right hand side I get this ik 2 times. So, that gives me a minus k square times whatever I had over here. Similarly, I can write what is the del p del t, right, and del p del t is then k square should be inside, yes. And then I take a del p del t. So, minus infinity to infinity del p tilde del t, because there is only del p, there is only term that depends on time. So, then I have e to the power of minus I k x dk and a 1 over 2 pi. And I know the del p, my diffusion equation is del p del t is d times this. So, d times this is d times this, which means that the Fourier transforms obey this equation, that del p tilde of kt del t is minus dk square, is minus dk square of p tilde kt, right. So, given this equation for the probabilities, the Fourier transform of the probabilities obeys this equation. Sorry, say something, which one? Okay. Okay, so this is the probability, this is the equation for the Fourier transform. But this equation you can solve, you know, the same quantity coming here, dy dt is minus something times y. Okay. So, this equation you can solve. So, p tilde of k comma t is p tilde of k comma 0 e to the power of minus d k square t, right. And all I need to then do is then, of course, if I am looking to solve a differential equation, I have to tell you what is the initial condition. So, let me take that same initial condition, my delta function, that is the probability that at time 0 it started from the origin. So, delta of x, okay, which means that my Fourier transform of this initial condition is e to the power of I k x delta of x dx from minus infinity to infinity, which is 1, right. Which means that my p tilde of kt subject to this initial condition is simply p tilde of k comma t is simply e to the power of minus d k square t, right, because that is my initial condition. And now, once you have the Fourier transform, you can just do the inverse Fourier to find out what is p of x comma t, right. So, p of x comma t is the inverse Fourier transform, is 1 over 2 pi minus infinity to infinity dk e to the power of minus I k x times this e to the power of minus d k square t, right. I just substitute for p tilde k t. What is this integral? Gaussian, correct. So, you just complete the square in k. So, you have a k squared term, you have a k term, you complete the square. What would you get? What should you get? Square root? 1 by square root, yes, 4 pi dt. So, you can check this, complete the square, that extra term will be this x square by dt. Normalize, check that your probability is normalized. And of course, in principle you could have guessed this, because we did the discrete random walk, and we got the binomial, we took the large time approximation, we got back this Gaussian. So, you know, you're guaranteed to get a Gaussian again because of the central limit theorem again. You can write this a little perhaps more explicitly. This is a conditional probability, in that I am saying what is the probability to be at x at time t, given that in this case I was at 0 at time 0, but in general you could say that, well, at time t0 I was at some x0, I was at some x0 at some time t0, and then you can just generalize this. So, this is just 4 pi d t minus t0, how much time has evolved, e to the power of minus x0 whole square by 4d t minus t0. So, it is just, I had this Gaussian here, I get back this Gaussian, except instead of getting it from the solution of the binomial, I have written down the continuum equation and I solve this continuum equation. You could of course calculate, now that you have the probability distribution, you could calculate moments. So, for example, what is the average displacement, right? What is that? That is just xpx. So, x times p xt given x naught t naught from minus infinity to infinity, right? What is the average displacement? We have the distribution over here, this or whatever, this, if you, 0, right? You have a symmetric random walk in this case, left, right. On an average, you have gone nowhere. You could calculate the second moment, x square. So, x square dx. So, x square p xt given x naught t naught dx minus infinity to infinity. And what would you get? Thank you. You stay at the origin essentially. Okay, what would this be? So, let me say, just to simplify, let me say I have started from 0, 0, 0. 2D, 2D, good, thank you. Because you spread out with time, right? The more time you wait, the more your packet sort of spreads out. What? I've just put 0, 0 over here. Starts at time 0, whatever it starts, I've put 0. Okay. This x square grows as time t to the power of 1, right. This is a universal feature of diffusive walks, okay, irrespective of the molecular mechanisms or whatever, irrespective of the microscopic details. Anytime you have diffusion, you will have your second moment x square, it grows with time as t to the power of 1, right. So, this characterizes my normal diffusion. Right. So, essentially again I start at some position at 0 with a delta function. As time goes, what diffusion does is that it homogenizes probabilities. So, you spread out as a Gaussian, sorry, that is not really a Gaussian. spread out as a Gaussian and so on. Eventually, if you waited long enough, if you were in a finite system, you would be equally likely to find your particle anywhere and so on. But in general, the width of this probability distribution that grows with linearly with time. Okay. So this is a characteristic of a diffusive work. If you had, of course, if you were moving with some velocity, right, then of course x would grow as time, x square would grow as t square, right. That would be a ballistic motion. For diffusive motion, it is goes as t to the power of 1. This is one of these universal laws that occur in many contexts, in physics of course, but also in biology. Universality, where if you calculate this x square, the second moment, you will see that this grows with time. This goes linearly with time. Very good. Okay, so let us think about this, right. So I had my one-dimensional random walk, right. So I could hop to the right or to the left. I calculate my second moment, x square. I get it grows as 2. Now let me make this a two-dimensional random walk. So I could hop to here or here. Okay. Each hopping is independent again. Okay. What would you and let me say that I wanted how much it has traveled in the y direction, 2 dt, right. So therefore, if I wanted a variance for this two-dimensional random walk as a whole, it would be the sum of the variances of this individual because they are uncorrelated, and therefore I would get 4 dt. In general, in any dimension, you would get d times 2 dt. But this universality would not change, it would still be t to the power of 1. Having said that this is ubiquitous, also know that there are always exceptions, and in biology there are many exceptions. So one of the ways that one characterizes exceptions to this is to say that if I look at the mean square, the second moment mean square displacement, x square, right, as a function of time, it goes with time as some t to the power of alpha, some exponent alpha, where alpha equal to 1 corresponds to your normal diffusive walk. But you could, for example, you are just given some experimental data, for example, and you calculate this x square and you see this alpha is something not 1. So if these are larger than 1, it could be larger than 1 or it could be smaller than 1. Larger than 1 walks are called super diffusive. Smaller than 1 walks are called subdiffusive. Now imagine, for example, as we are saying that bacteria shows this run and tumble is a classical sort of random walk, and you will see diffusion. But for example, now imagine that I have a cell, and I have a protein. I have some cell, and I have some protein inside the cell that is doing random walk. So it's trying to go and find for some target, maybe some other protein to which it goes and needs to bind. It's trying to do a diffusion inside this space. But but like we showed last day, inside of a cell is very crowded. Multiple other proteins, ions, this, that, organelles, so it's very crowded. So when it is doing this sort of a random walk, it is not doing in free space, but it is doing in a space which is filled with these other molecules, crowding agents. And in that case, for example, of course, you could have two things. You could have it does diffusion, but it does diffusion with a diffusion coefficient that is smaller. So, right, because you have many other obstacles in its path, and therefore the diffusion coefficient is smaller. Or what is more often the case, at least in these biological systems, is that you will see that this exponent changes and you get subdiffusive walks. So subdiffusive walks are often very common inside these crowded sort of systems where you have multiple other crowding agents that obstruct your random walk. So, at some point if I get time towards end, we will look at some general theories of these. These are called anomalous diffusion if you have alpha not equal to 1. So, we will try to look at some theories for anomalous diffusion. Super diffusion. No, so 1 I said that if you calculated this x square, you could find that you still get a t to the power of 1, but this diffusion coefficient you see some d prime, and this d prime is smaller than what you would have expected in free space. So, you still move diffusively, but with a smaller diffusion coefficient, right. That is one possibility. The other possibility is that the nature of the walk itself changes and it becomes subdiffusive, and often in these bacterial sort of in these biological sort of motion in these crowded environments, you will see these subdiffusive walks. So, let me write these somewhere. So, we derive the diffusion equation as the continuum limit of a discrete random walk. So, del p del t d del 2 p del x2. We solve that p of x comma t is 1 by square root 4 pi dt e to the power of minus x square by 4 dt. We calculated the mean, which was 0. We calculated the variance, which was 2d dt. Right. So, the picture. So, when we started this sort of random walks, our picture was like bacterial motion, for example. So, I have a bacteria. At every time it takes a step, let us say over here, then next time it takes a step, next time it takes a step, next time it takes steps, maybe it comes back and goes this, whatever, something like this. You start off at some position 0 at some time 0, you do your random walk in 2D, 3D, 1D, whatever, you reach some other position, okay, some x at some time t. And then this path that this bacteria traces out, if you were to quantify, if you were to look at bacterial trajectories or protein trajectories or whatever. So, these paths that it traces out in time is my random walk, right. So, that is my picture. On the other hand, you could think of these paths as not in time, but in space, right. So, I say that I have, let us say, one rod. I choose, let me think in 2D. I choose whether to put it horizontally. So, I place this first rod some direction. Then the next rod I can put like this, I can put like this, I can put like this, I can put like this maybe. So, maybe I choose this, then the next rod I choose and so on. So, I am putting these rods in space, right, something like this. So, which looks exactly like this, except this is a time trajectory, this is in space, and then what I would get are physical polymers, for example DNA, right. So, this same sort of a model that I have, or the same sort of a mental picture that I have of random walks, if I think of these as random walks not in space, sorry, not in time, but in space, I could generate conformations of polymers, right, and these would be random walk polymers. So, these would be random walk polymers, right. So, what do I say? So, I say that I am in this 2D lattice, I am in this 2D lattice, let us say with lattice constant A. So, every time I take a step, I place this bond essentially. So, this is, think of this as a bond, and this bond has a length A. Next time I place another bond, it has another length A, and so on and so forth, and I do this random walk in this space. At the end of the day, what I have generated is essentially some sort of a curve in space, if I zoom back far enough and look, and that is like a polymer, my DNA, my chromatin, whatever, proteins, whatever, some polymer that I have generated. And I could ask that, so if I summed up over all of these displacements, each of A, right. So, if I summed up over all of these displacements, right, sum over I would get the end-to-end vector of this polymer, right. So, I have individual displacements, let us say of n steps. So, I equal to 1 to n. I get this end-to-end distance of this polymer that I have generated, and then I could ask that, what is this average size of the polymer, what would be this average size of the polymer? If all bonds were symmetrically chosen, I could choose any 4 or whatever, in 3D any 6 with equal probabilities. What would be this R? This average R? N raised to the power of half. Okay. Anyone else? Yes? Shomo? Even better, let me think of this polymer as a 1D polymer. So, I either place a bond to the right or I place a bond to the left, and at the end of the day, I get some sort of a 1D polymer object. Overlapping bonds, of course, doesn't matter. And then I count what is my end-to-end distance and the average of that. Yes? 0. Why this and not this? Who said? Shadina, you said? No, you said. Why the Sapna, right? Shweta. Why this and not this? When is this? So, the second moment indeed would grow as n. Okay. So, if you are looking for n to the power of half, that is the square, that is the root of the mean of the square. So, root RMS, right. But just the mean, that is not n to the power of half. So, just because this is true does not mean this is true. The mean is always 0. So, not this. The mean is always 0. The RMS is n to the power of half. Yes, it is one measure of the size of the polymer. So, you could think, okay, then finish. Absolutely. So, so what I am calculating over here is an end-to-end vector. What Siddharth, right? What Siddharth is arguing is that you could have this polymer, whatever, a very big polymer, but finally the end has come over here. So, this end-to-end vector is just this, it's very small. And in that case, this vector over here would not be an accurate representation of the size of the polymer, which is still quite big in that sense. And absolutely correct. So, but also not. So, what is a more well-defined measure of the size of a polymer is what's called the radius of gyration, which means that you take each of these position vectors. So, you have you have many monomers in this polymer, right. You take each of these, you subtract the center of mass, then you square this, take the average of this, and that would be some sort of, that would correct. So, that would be perhaps a better measure of your size of the polymer, and indeed this quantity is called as the radius of gyration of the polymer. It is called as the radius of gyration. However, you can show that at least for these sort of polymers, simple polymers, it is just some multiplicative factor times the end-to-end distance. So, if you are looking at scaling, that how does it depend on the size, all these two quantities would differ by would be some prefactor. Okay. So, exactly, so therefore, in this case, although this mean end-to-end vector or this mean size is 0, the root mean is some n to the power of half, and this is in fact a better descriptor of what is your polymer size. So, what you would say is that your polymer size grows as the square root of the number of segments, the number of monomers that you have. So, just like when you had random walks in time, your dispersion, the second moment, grew as the square root of time. If you think of this random walk not in time but in space, and then that object would become the size of your polymer, and that size would then scale with the square root of the number of subunits in that sense. Okay. And again, you could ask that, well, so again, if I try to think about a very simple polymer, in 1D, if I try to think of this 1D polymer. So, I take steps either to the right or to the left, right, with probability half and half. At the end of the day, after I have taken n steps, I have some end-to-end distance r, and I could ask what is this probability of this end-to-end distance being r, given that I have n steps. Okay. And what would it be? It would be simply a binomial, right? Exactly like we did for the discrete random walk, it would be a binomial. So, n c. So, essentially you have to take some number of right steps, some number of left steps, and then you will have the number of right plus the number of left must be the total number of steps, whereas the number of steps right minus the number of left times the size of each step would be your end-to-end r, and then this would be nc one of these nr, which essentially means that if you work this out, so this would be n plus r by 2, right, and half to the power of n. Just like I had p to the power of nc, not that, n by 2 plus r by 2a. So there is a factor, n by 2 r by 2a. So I have to get it to a number. You would get the binomial as you would expect, because you have done the discrete random walk. But now you can take the continuum limit of this. So if you had a very long polymer, and by long what I mean is that the polymer, the number of units or the number of monomers in your polymer is much larger than 1, or the length of the polymer is much greater than the size of each individual subunit, then this probability would become a Gaussian. Again, exactly like we had in the random walk case, this probability would become a Gaussian. And again, this you can do explicitly by taking Stirling's theorem, like applying Stirling's formula to all of these n factorial terms, and what you would get is an e to the power of r square by 2 n a square 1 by square root. Let me see if I have all the factors correctly. 2 pi a square, yes. So 2 pi n a square. Okay. You would get a Gaussian. So it's exactly the same mathematics. It's just that how I think about these things, how I think about these quantities changes. So here earlier when I was thinking of random walks in time, my variance was of units of time. What came here was t. Here it is the number of subunits that I have in my polymer. So what comes here is n, and of course the size of each individual polymer. Okay. But the central limit theorem is the central limit theorem. There is nothing to do about that. Similarly, you could now, if this was a polymer in one dimension, because I just did right and left, you could do in any dimensions. You could do in 3 dimensions, for example. You would still have central limit. So therefore, your probability distribution would still be a Gaussian. So you would have probability 3D of r comma n would be e to the power of minus r square by 2 n a square, 3 times this, okay, 1 for x, 1 for y, 1 for z, and then appropriately if you do the normalization, 3 by 2 pi n a square whole thing to the power of half. Not half, sorry, 3 by 2. So you can do this and check, because once you know that you will have a Gaussian, okay, you can then just use the normalization and you can use the weight. So you can say that I know that integral p 3d r comma n dr has to be 1, right, because my probabilities have to be normalized. And I know that my r square p 3d of r comma n, so this is my variance, second moment, right, not variance, second moment, r square, this dr, this is n times a square, right, because that's what we said. it grows with n. Once you know this, just as long as you know, so it's some normalization constant times this Gaussian form, you can work out what is this Gaussian form and huh? Yes, thank you. Absolutely. Okay. So we're thinking about these walks in space, walks in time. We change our frame of reference to walks in space. Instead of trajectories of bacteria, what we get are shapes of polymers. Okay. The underlying theory is exactly the same, but we have looked at two completely very different things. Here we are looking at physical objects which are polymers, and the probability distribution of that, if you have these sort of polymers, random walk polymers, or these are called ideal polymers. These are called ideal polymers. You have worked out the probability distribution of these ideal polymers, which means that you know statistically everything that is there to know about these polymers. These are certain implications for polymer properties as well, but today, okay, time is up. It would be nice if I had finished it today. Okay, I'll just talk a little bit more about this polymer aspect next day when we meet back on Monday. Okay. Okay. Thank you.